let you know.
Okay.
Hello everyone. Welcome to the Biomed Colloquium and to our first talk of the fall semester. We are pleased to host Professor David Bortz from the University of Colorado Boulder. He earned his PhD under Professor Banks at the NCSU and held a postdoc position at the University of Michigan. His research centers on data-driven modeling, scientific machine learning, and weak form method for dynamical system. He has made influential contribution in mathematical biology from cell migration and biofilm to the infectious disease dynamics, including the COVID-19 policy modeling. Today, he will present the weak form is stronger than you think, introducing the power of the weak form approach in learning from complex and noisy data. Yeah, please welcome Professor Bortz.
Thank you for the nice introduction, Jay.
Mhm.
So as you said, I was a postdoc at Michigan, so of
Yes.
course I knew Danny
Yeah, great.
when I
University.
was there, and so always heard great things about you every time I ran into him. So
Thank you.
Um, all right, so I guess without further ado, I'll start here. So where this came from, and the whole point of view here is if you are familiar with, say, the weak form in mathematics of studying, it usually studies in PDEs. So when they study shock waves, they multiply by a smoothing function. And then they can use that to figure out, existence, uniqueness kind of proofs for PDEs, equations. And it also, on the computational side, you can do that and it will lead to something called the finite element method. So if you heard this is a fairly, usually very common they teach in numerical methods classes. But one of the things that happens is that when we look at, say, the finite element method, we only think about using it to solve the equation. Okay. And so you would say, I have some parameters, I have some initial conditions, I have a discretization for the finite element method. I will solve the equation now. Okay. This approach of weak form scientific machine learning, we are flipping that on its head. So we are going to do the opposite problem where we say, instead of solving the equation, I'm going to assume I have data. I'm going to plug the data into this weak form version of the equation, and I'm going to try to solve for the parameters, or I'm going to try to solve for the initial condition. So it's sort
David,
of the
I'm
opposite
sorry. Are
direction.
you moving the slide or not yet?
Not yet. Not yet.
Okay,
I will.
gotcha, gotcha. Yeah,
I will.
good, good.
Yeah.
Yeah.
I'll do it in just a second. Yeah. I just wanted to say that is that you think about it, the weak form is coming from finite element method, or that's where you think about it, but we're doing the opposite of what you would normally do with the finite element method. So that's just to start off the talk. I just want you to have that in the back of your mind. And here is really I'm gonna talk about a very simple example here, but it really demonstrates exactly what we're doing. Okay, so this is the logistic differential equation. We all know this one. It's a beautiful equation. It has a nice solution there. And it's a function of the parameter r, the parameter k, and of course the initial condition. And a lot of times in biology, you have this type of a model. You have a saturation effect, and maybe you have small amounts of data. Now, what do we do in these cases? Is we would try to set up a nonlinear optimization problem as a function of k and r, and maybe u naught. And if you didn't know that, and if this was a more complicated equation, then you would think about doing a numerical approximation. And this is the way we teach people to do modeling, that
Mm,
we do parameter fitting via either using this analytical form if we're lucky enough for our models to have that, or we do a numerical solution.
mhm.
But we're always doing this nonlinear optimization as a function of r, k, and whatever other parameters you have.
Mhm.
And so the problem here is we don't realize there's a lot leveraged on the step size that you're using, the specific tolerances of the solver, the type of optimization algorithm you're using. Are you simply fitting to the data with the least squares, or do you have something more sophisticated in terms of accounting for the noise? These are all very valid questions. And you can use this type of a system, or I mean, 100 3,000, whatever, 10,000 dimension ODE, you're still going to we think about these very similarly. Okay? What I am going to suggest is that we look at this differential equation of u dot equals
Mhm.
W1u plus W2 times u squared. And what you see here is a differential operator acting on U, and then you have linear in the parameters.
Mm-hmm.
When we have linear in the parameters, let's not let this go. If we go back over here, we've got nonlinear in the parameters that we have to deal with.
Uh-huh.
So what I'm going to do is I'm going to suggest, and we are working through a way to think about this problem as a linear problem,
Mm-hmm.
which is much easier to solve. And we have, 70, so years of computational science dealing with solving linear systems. So that's what we're doing. Everything that follows is noticing that this is in a linear system and how do we deal with this?
Mm-hmm.
Okay? So the first problem that comes up, of course, is that derivative.
Mm-hmm.
So one of the things you might do is you say, well, what do I do if I need to take a derivative of data, right? I'm going to take this a finite element version of this, but I need to still plug in the data. The great part about it is you do finite element and you can take that test function and do integration by parts, and that derivative migrates over to the test function. So
Mm-hmm.
you no longer have to think about a derivative of data.
Mm-hmm.
So that's a huge issue here. When you start thinking about noise that will come in this U variable, I don't know why this T is in a different font. That shouldn't be, but it's you think about that. Well, you're actually doing some smoothing here. So you're actually implicitly in this method is taking care of, or at least addressing the fact that you have noisy data. Okay, so this now, once we have it, we have a linear system here. If you take the data and you plug it in, you've got something you can operate on here. You can evaluate this, you can evaluate this, and you can evaluate this over here, and you now have a system that's linear in W1 and W2. You can relate those back to the growth rate and the carrying capacity, et cetera. But I want you to notice here that this is linear. And of course, we're going to choose a test function, so I don't have to do that evaluation part of integration by parts. So this part goes away.
Mm-hmm.
Okay, so this is again the core of everything that's happening. All right, so this is an interesting way to think about it, but there's lots of things that we ask from modeling, right? We ask from modeling, how do we know it's the correct model? What is the impact of the noisy data? A lot of the times, if you have to do these nonlinear optimizations, what is the initial guess that you're going to come up with to try to optimize? That's a very challenging problem and one that doesn't really get as much respect as it should. What is the impact of using numerical discretization? We have many examples of when we tried to use these, solve a PDE and fit a PDE using repeatedly proposing different parameters. It depended upon which numerical scheme you used and what was the step size. So there's all sorts of things that can go wrong here. And so this is what we're trying to tackle is basically all of these at the same time. And so I'll show you what's going on. But first, let me just acknowledge the people that sort of are making this happen. So Dan was the first person that worked on this with me. A lot of this came out of his dissertation. He is now a director's fellow, a postdoc down at Los Alamos. And then April and Seth are current grad students, and Nora Rainey and Christian are current postdocs. And then Vanya Dukic is a professor in the applied math department. She's a computational statistician. And so between Dan and Vanya and I, this is sort of form the core of a lot of these ideas where they came from. There's a few other people that have joined the group more recently that I don't have pictures for, so they're listed on the lower right: Moyi, Abi, Will, and Jack and Nick. Okay, so where did this come from? And surprisingly, it actually goes all the way back to the 50s. And this was at the dawn of computational science when computers were actually getting to the point where they were usable in scientific contexts. In particular, this was in engineering context. This is in the aerospace industry. They were looking at high-speed parameter estimation for, these new exciting technology of jet engines and fighter aircraft. And that's what they were trying to do, is they were looking at this. And they ran into all the same problems that I just talked about. They took some differential equation, they plugged in the data, and they, said, well, I worry when I try to have to do a derivative of my data. And
Mm-hmm.
sure, I can plug in all of these, maybe this is u, maybe this is u squared, maybe it's something else. I can, use all of those f features and evaluate at all the different time points. I have a beautiful regression problem. It is incredibly unstable. It is super fast because you're
Yes.
just, solving the least squares problem, but it's very sensitive to noise.
Yes.
And so there was ways that they tried to deal with it, but at the end of the day, this approach of plugging data into the equation and looking at an equation error versus what they used to call it output error. We're trying to call it solution error because I think that's sort of a very nice way to think about either the solution error, where you're comparing the solution of the equation to data, or you're taking the data, plugging it into the equation, and looking at the equation error, like the residual of the left side minus the right side, this GW minus B idea. Okay. Um, People made a choice. Solving the equations was a way forward. There seemed to be some mathematical problems with doing this plugging in the data, this equation error approach. Well, you'll see what happened. But anyway, but this is sort of where it came from. Fast forward to 2016. That field, it wasn't that it was dormant. It just was not as it wasn't very active. There were many areas of it where there just wasn't anybody publishing anything.
Mm-hmm.
Whereas, of course, forward solver based methods of modeling was everywhere. And then in 2016, Steve Brunton, Josh Proctor, and Nathan Kutz published this paper in PNAS,
Same.
which in some sense resurrected the idea.
Mm-hmm.
And what they were doing wasn't just taking the model and modeling and using it for parameter estimation. They were going a step further. And what was really amazing about this, and this is amazing work, where they took all these different potential features,
Mm-hmm.
candidate features, and rather than having to say, choose all combinations of these to create all possible models and solve them, they said, no, 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 we'll just have one big model. We'll plug the data in and we'll try to prune it and
Mm-hmm.
choose which terms are actually there. So if you were trying to say you had data from what you thought was the diffusion equation, what you would hope would happen is that you would be able to solve this sparse regression problem for W, and W would come back as a 0 in the first entry, 0 in the second entry, non-zero here, because that's the diffusion, you need the second derivative, and then everything else is 0.
Mm-hmm.
So there's sort of two things going on. You're learning the parameter, if it's there or not, and then the value itself. So it's sort of doing two things at the same time. This is different than what's happening here. This is they're just doing parameter estimation. They know the model.
Mm-hmm.
Here they're saying, let's learn the model. And
Mm-hmm.
those are, when I say scientific machine learning, those are the two problems that we, at least in the weak form scientific machine learning, are trying to tackle. Either what is the model, or given the model, what is the parameters? They're related, obviously, but anyway, I'll talk about a little bit more about that later. But anyway, so this was the idea, but they ran into the same problem that the people in the 50s did. Derivatives are unstable. You do finite difference operators, it is going to go poorly. And this is the sparse identification and nonlinear dynamics paper. In the Cindy paper, they admit this. There's not any secrets about it. There's just, how do you deal with it?
Mm-hmm.
But this whole, I mean, you think about it, if you have like n different models here, you are implicitly, by saying and by going through the process of sparse regression to say whether or not you have them, you are exploring the space of like 2 to the nth models, and you're pruning it down to the model that is statistically supported by the data, which is, I mean, that's a big model space if you think about that, that you're trying to process. So it's a really, really nice piece of work. Okay, so this is where we came in. And this was in 2021 with Dan's work. And if you're more on the biology side, this is all the important part is that we have a way to get back down to doing a nice regression problem.
Mm-hmm.
What we are really doing is this test function here. You can think about it like a smoother. That's an easy sort of intuitive way to think about it. We spend a lot of time choosing it very carefully because everything matters in terms of if you choose that correctly, things work. If you choose it poorly, you're going to think this method doesn't work at all.
Okay.
So what you do is, and this is just sort of abstracting the derivatives into time derivatives and then all possible time and space derivatives, and
Mm-hmm.
then you do integration by parts to pull the
Yes.
derivatives over to the test function. And then
Mm-hmm.
you can reevaluate to create your G and W again, and then you solve a sparse regression problem.
So, David,
Okay.
when you do this,
Yes.
you use a specific test function, or you use the many test function?
I'll get to that in just a second.
Okay, gotcha.
So just to give you an intuitive idea of what's happening, the test function is something like what's on the left here. Okay. And you'll note that it is, I mean, obviously you can stretch this, you can make the domain wider, you can make it narrower, you can make this smoother. There's all sorts of strategies, and we have some of them. A lot of our research is actually focused on how do you choose the test function to
Mm-hmm.
get the output that you want, whether it's equation learning or parameter estimation, like what's the process? But at the end of the day, there's a couple of features that are really important. It has to be very smooth,
Okay.
and it has to be zero at the endpoints. So far, there's ways to get around this, but that's sort of an active research area. So I'll only talk about it under this restriction. So it has to be zero at the endpoints. Not only that, it has to be a zero derivative at the endpoints. And I'll talk about why later, but it's really fascinating that that's actually a restriction. So you'll see it's super smooth and super flat because the value and the derivatives, a whole bunch of derivatives are all zeros. But so this is the test function. This is you just think of like a smoothing or a smudging or type of thing. This here is the derivative of this picture on the left. So this is what you multiply all the terms. Say if you have an ODE, all the terms on the right. This is what you multiply the variable on the left, which gives you a weak first derivative. And you can actually, if you squint at this, if you, it says a negative sign because it's integration by parts, but if you flip it upside down, the negative, you can see it's actually the continuum analog of a finite difference operation, where it's sort of positive to the right and then negative to the left. It's almost like, forward minus backwards divided by the step size. It's kind of what's intuitively going on here. But so we use these, and then we plaster them all over the domain. And every one of these test functions creates a new row in our regression problem.
Mm-hmm.
So it's like you're taking your model and zooming in on one part of the domain where the data is and seeing how valid the equation is there. And then you go to another part of the domain and you keep doing that. And
Mm-hmm.
this is creating all the rows in your regression problem. And the same thing down here. These are all the derivatives of the test function. So
Mm-hmm.
is that Jay, is that answering your question
Yes, it's
a little
perfect.
bit?
I think,
Okay.
yeah, very beautiful.
Okay. So a lot of our research is on the methodology of choosing radius, smoothness, shape, what's the spectrum, and the Fourier domain, those kind of questions. But the thing that really set us on this direction as being very compelling was we noticed you could do this for PDEs also. And so if you just take test functions and multiply them together, they're just sort of,
Mm-hmm.
multiplicatively like just a product.
Mm-hmm.
You can create test functions in time and space and one space
Yes.
dimension, two space, whatever number you want. This is just an example of the kinds of test functions you could use that would give you, this is the smoother that gives you just the value of the function. This one here will give you a derivative in time. This one here will give you a derivative in space. And this one here will give you two derivatives in space. So you can see that this is a very natural way to extend this to higher dimensions of in PDEs and higher order derivatives. And so yeah. Okay. Um, so I'll just throw this up here because we're using the phrase scientific machine learning. So I throw a machine learning picture up here. So what this picture is showing, and the reason that I'm also showing this is that we have gotten some amazing speed ups by recasting some of these layers as convolutional layers in a neural network. And so you can use PyTorch to accelerate your computations by actually another order of magnitude. And so the example here is you start with data. This is actually a Swift-Honenberg
Mm-hmm.
PDE, so like a pattern formation PDE.
Mm-hmm.
And this is WCindy. So you propose a whole bunch of candidate terms. U1, just u to the first power, u to the second power, third power, fourth power, whatever features you want. And then you pass it through the convolution layer with the test functions. So you sort of, and you can see all of them go to all of the test functions. And this one is just the test function convolved with the data or sorry, whichever of these polynomials you want. This one, you can kind of see, we tried to have the picture here. This is the test function that's the derivative in space. Here's the derivative in the other space. Here's the Laplacian. Here's a bi-Laplacian. You pass them through all of these layers, which are just
Uh-huh.
convolutions, and you use that to generate the regression problem.
Yes.
So then you use G and B, and then you do a sparsify step, and you finally get W. And now you have whatever W is, this sparse W, it tells you the learned weak model.
Mm-hmm.
So this is just supposed to be a set of the polynomials that come out, and then there's the Laplacian and the bi-Laplacian
Oh.
that are the two terms that come out, or
Mm-hmm.
the two features of the data.
Yes.
It's still in the weak form version of it, but
Yeah.
nonetheless, you can now read off what you think the model might be. So
Wow.
this is and it's and in some sense you can argue that this is interpretable AI, right? Because you
Yeah.
understand this every step. Every
Yes.
step is mathematical. You can go forwards, backwards, whatever you want. You can say, I can improve the numerics here. I can think about statistics here. I can, like, it's actually explainable.
Yeah,
It
yeah, yeah.
breaks it all down. So, that's one of the reasons why we're excited about this, of course.
Ah,
Mhm.
it's beautiful indeed. So basically, for the taking a derivative for the given discrete data is very noise sensitive and dangerous, but we convert all that derivative to the known smooth weak form solutions, test functions so that we avoid all the derivative issue.
Exactly.
Yeah, wow,
Exactly. It
wow,
just
wow.
completely bypasses it. And
Yes,
you don't have to solve the equation. So you're bypassing that too. So,
yes, wow.
okay, so what kind of performance can you get here? And this is
Mhm.
some really compelling things. So this is not a biology problem, right? This is the Lorentz attractor.
Yeah, yeah.
Um, but you can see here that with this kind of noisy data, is 10% noise, we
Hmm.
can just turning the crank on. Not even this is from 2021 now. Not super sophisticated. 10% noise gives you less than 1% error in less than it's like 0.02 of a second to do this just in MATLAB because
Hmm.
you're just solving a regression problem. It's really fast.
Okay.
Like how do you even think about comparing with a forward solver based parameter estimation here? Like if you want to get I mean it's Lorentz, you have to crank the tolerances down so low that I mean if you want to get really good accurate forward solves and then optimization on top of it, it takes forever. It's not a feasible way to approach this problem. Um, the really awesome thing now is we start going to PDEs, and I'll talk a little bit more about this later. This is again, this is not a biology problem. This is actually from a laminar flame front and a fusion and
Wow.
combustion and basically things exploding. But it's an awful equation because it's got like a fourth derivative. It's got a polynomial in it, and here we are. This is what the solution is if you do a really high accurate numerical solve. We added noise to it, and you can
Uh-huh.
see the various noise levels. We can go all the way up to 50% noise, a 50% noise ratio. 100% of our experiments get discovered correctly. These three
Wow.
terms pop out of a big model or a big
Uh-huh.
set of like several hundred terms.
Uh-huh.
Yeah, there's ways we can improve the parameters. They weren't great in the 2021 paper, but the fact that we can go so high in noise and get recovery and discovery of the correct equation is kind of compelling. So, okay, I don't want to go through a huge number of the algorithmic details, but I will say this whole idea of multiplying by a test function is not new. What is new is making it work. That's the trick here. So there are people going all the way back to the 50s that have proposed different forms of test functions. And so the question is, what did they miss? Why did this not take off as a method? There was actually even a review article in 93 where they were basically lamenting. They don't understand why more research hasn't been done in this area. Part
Uh-huh.
of the problem was simply they didn't have access to 21st century applied math and statistics. They really didn't. Like there's simply some advances that have happened in numerical linear algebra and statistics that weren't available back then. And that's it. And so we're
Mhm.
fortunate to have them
Wow.
to build things off of. And so this is one of the first things that we saw that really sort of said, okay, we need to think about this a little more deeply. So this is a Vanderpool oscillator. It's just a simple nonlinear oscillator. And the test functions we started with here were piecewise polynomials. Okay, so they have a radius a, and then they would have a power p. So here's the thing that and this was actually we made a mistake. We accidentally left the power too high. But what happens is you crank up the p and look at the error, the relative error in the parameter estimates,
Hmm.
it just collapses to basically machine precision. And anytime you see something giving you machine precision results
Hmm.
in fractions of a second, you take notice, right? This now there's no noise here, but
Hmm.
this is weird. This is not what you would normally think of as being able to do parameter estimation or equation learning and get machine precision.
Okay.
Turns out there's a reason for this, and it has to do with these integrals. And you can show that basically the integrals, the error in the integrals, you can go
Uh,
back to Euler-Maclaurin
yeah.
and find out that it's basically the smoothness
Mm-hmm.
dictates because it's basically a periodic function. And using trapezoid rule, you get this amazing accuracy. it actually falls apart if you try to use Simpson's one third, but it's amazing for trapezoid. That's a there's a lot of research going on around this, but that's basically the core of it is that these are integrals that are being they're numerical quadrature. And it turns out that if you use trapezoid rule in this way, you can get spectacular accuracy.
I
And
see.
that's why you get machine precision. So
Cool.
it's,
Wow.
it's cool.
So
It's so
kind of
surprising.
basically trapezoid rule for the integral is basically very accurate.
It is. It
This
is. And
test function.
there are other methods that we're exploring that
Mm,
are not ones you'd expect. But
mm.
that's a future paper that we're doing.
Gotcha. Wow.
So yeah, so it's this was surprising, but it sort of gave us the first inkling that there might be something interesting to talk about here.
Hmm.
Um, I actually didn't want to talk. I'll talk about this one.
Hmm.
So this is a different way. I'm blowing through more time than I thought, but here's a different way to choose the test function. And what we're doing here is this is for that nasty equation that has a fourth derivative, and here's the blue line with red noise. Okay, so the question is, what do you do? Well, what we did with this was we looked at the Fourier transform, went to the spectrum of the noise, and
Hmm.
we figured out how to match the spectrum of the test function with the spectrum of the data so that it filtered noise in the
Hmm.
convolution.
Hmm.
And basically, what that means is now you look down here, this is a comparison between the clean and noisy weak fourth derivatives in space at a certain time snapshot. And it's, they're lying right on top of each other. It's really surprising that you get that great. I mean, it's a fourth derivative. You're able to take a fourth derivative of data, which is
Wow.
it's cool that it works out this way. Okay, so then this is all in the JCP article from 2021. And you get these great results, right? In the sense that the wall time is nothing more than 75 seconds on a whole laundry list of PDEs for reaction diffusion, porous media, Navier-Stokes. You can learn Navier-Stokes from like a 3-minute video of flow past a cylinder in like 12 seconds on a laptop, which is, yeah, how long did it take us to come up with Navier-Stokes? And now you can do it in 12 seconds just by watching water flow. Um, anyway, okay. So again, comparisons are weird. So here's the thing what the tool, the technology, the workflow that we're building here has this. It's a very interesting capacities because you have very fast equation learning and very fast parameter estimation. And so, what do you do with this? Well, one of the things since this was originally funded on a cell migration grant, we started looking at cells that were migrating. And so, this is a picture of the experiment and some of the original models that we came up with, the green dots being the tracked cells and the blue being the projected models here. Now it's not perfect. It's just these are Hackett cells. I think they gave them some endothelial growth factor, some EGF, to watch them grow, and then you can track the nuclei using a different tracking software.
Hmm.
So what we tried to do is we said, okay, we could put a PDE together that tries to describe this, but how about we try an individual model for each individual cell? Let's see what the force potentials are that the cells are using. And the first pass at this gave us attraction repulsion, alignment, and drag potentials. And this is saying sort of don't get too close or behind me. I don't care if you hang out side by side. This one is saying I only care about what cells are like in front of me. I will follow front cells in front of me, but I don't care what goes on behind me, basically. And these are potentials. And so what we did, there were some issues with the data. They just redid them. They did some other experiments, and I'll talk about those in a second. But these were the potentials that came out. And so we said, can we distinguish between different, artificial data? Can we just, if we have a species that has these three potentials versus just this one or this one, could we actually sort the cells, right? I mean, sorting cells is a big deal. What we're going to do here is we're going to here's the trajectories of a bunch of artificial cells, and we will learn the interacting particle system model for an individual cell. And what you can see here, I've never seen results like this in the sense that you have a cell that's wandering around. The black is the data, and the blue curves here, that's the prediction. So you see that this is the prediction, the model you get out is able to accurately reconstruct a 90-degree turn followed by a 180-degree turn in the cells. I mean, these are just surprising that it's getting this accurate. You can go beyond it and sort the cells. And so now you can take your spaghetti mass of cells that are completely unlabeled, learn the models for every individual cell. So if you have like 1,000 cells, well, it's a completely parallel process. You're learning the cells based upon the movement of the nearby cells, and then you can sort those into different categories of behavior. So this is sort of a, foundations for biological digital twins. It's very compelling to do that. Pushing forward with it, this is actually three snapshots of a cell migration. And they basically, you have a sheet of cells where they scraped away. It's a scratch essay. And so you see the cells migrating into the middle. And in particular, we're going to focus on this fingering that's happening. We'll zoom right in here. This is what the trajectories look like of all of the cells in that area of the data. We're going to focus on track 1798, use our nice interacting particle system model with attraction, repulsion, alignment, and drag. And you can zoom in here. These are the potentials that come out. But for this cell, which is in the middle, so there's lots of data for it, you can see the blue prediction is following it surprisingly well. And it's, the circle is about the size of the cell, and yeah, it's got that repulsion in the front, but it also has attraction to the left and right. And then there's a little bigger alignment potential that's being learned here. And so we're learning these potentials. Basically, when I told my biochemistry collaborator this, he's like, "You just rediscovered that cells are polarized when they're moving," and which is, it's very interesting that you can actually learn where potentially the sensors are on the surface of a cell, where the movements are being generated from. So, are there questions so far on this? Is this making sense?
So any question, everyone? If you have a question, I think please feel free unmute and then ask a question, or you can also leave the question in the chat room.
Oh, can
Okay.
I have just one simple
Sure.
question? Oh, so in that experiment, how many particles did you use for the parameter estimation?
For this specific one?
Yeah.
Let's see. So there's three potentials that we learn here. Each one of these, we're using circular harmonics to figure out the radial potential. My recollection is that, so at that point you're trying to do like function approximation of the potential.
Hmm.
So I want to say it was something less than like 20 or 30 parameters, somewhere around there, if I remember correctly.
So it's for each particle you invert 20 to 30.
Yep.
I see.
And then afterwards, you can do post-processing that sorts the cells into different categories based upon
Okay.
the models that they have.
Thank you.
Okay, so we're kind of excited because this is telling us that we can discover movement models for cells based upon their trajectories. Now, I will say, of course, it's not perfect, right? The reason we're able to learn this cell trajectory is because it's kind of in the middle of the finger, and there's a lot of interactions with nearby cells. The cells that are like way, I don't know if you can see my pointer, but the cells that are like way over far away, moving by themselves, it's very challenging to learn the models because there's just not interactions from one cell to the next. And so what the potential is there is less clear on how to estimate that. But for a cell that's kind of in the middle of the pack that has a lot of jostling and interactions with nearby cells, that's easy to learn. And these each one takes like at most a second to learn. So you can do it perfectly parallel. So it's basically that on a GPU works really nicely. Okay, so that's our sort of biological digital twin angle, and that's the equation learning. Let's dive back into parameter estimation because I think this really has some interesting and applications, especially in systems biology. Okay, so effectively, what's going on? Actually, let me just go to this one. So we create the regression problem. This is what we do with our the test functions, right? We convert everything to the G matrix and the B matrix, and one of the things that we have seen in the literature, and even in the Cindy world, and where you're just plugging data in, is there's uh, I don't know if it's not aware or just this isn't taught much in statistics. The problem when you're trying to solve this regression problem is that you have your data, and the data is impacting both the matrix
Hmm.
and the vector.
Yes.
Okay. So if you are make just like a simple assumption, if you say it's truth plus noise is impacting the matrix and the vector for regression. The way this impacts is that if it was only affecting the vector, you'd have ordinary least squares, which is what we usually teach in linear algebra, right? Where you have these vertical displacements from a straight line. The problem is you have this situation, which is
Uh-huh.
called an errors and variables or total least squares. And
Uh-huh.
so that was the whole agenda for the Bulletin of Math Bio paper that we wrote was how do we fix this so that we can get good estimates? And the way you fix it is by correcting the covariance for the system. And basically, this is everything else here is just bookkeeping. This right here says take some derivatives of the features on the model. That's kind of the core of what it's doing, is it's correcting it using a derivative
Yeah.
of the that. And of course, it's a weak derivative, but it's still a derivative there. Okay, how does this work? Pretty darn well. So this is Fitsunagumo, which we know has some really oscillatory behavior. It's difficult if and this is just we just used off the shelf whatever was default in MATLAB, and this is the wall time versus the relative error of the parameter estimates. And if you want to do forward solves with good accuracy, it can take, a while to get really good parameter estimates if you put the tolerances where, you'd expect. But with the Wendy, this is taking, I mean, it's solving the same problem no matter which realization you have, which noise level you have, and it's getting it down in fractions of a second. And it's usually so in our experience, these things are usually about 2 orders of magnitude faster and an order of magnitude more accurate, even in the presence of noise. And this is 5% noise here, and we're getting things down, below between. Oh, that's what. This is the 10% error line, so it's something, 5% and lower. This is about, 2 or 3%. So is the median here, that triangle. So it's working very well. The really awesome part about this is that because it's a regression, if you know something about the noise structure, so you assume like it's Gaussian, additive Gaussian, you get the uncertainty in the parameters for free. That's
Mm-hmm.
just what happens when you do regression. You can compute these things. And so you can get all the covariance matrix. This is just for 20% noise with Fitsunagumo. And you can just write down or compute the covariance matrix in a very straightforward way.
I see.
Um, okay, so this is all great. This works really well.
Mm-hmm.
I will say this is an active area of research. Okay, so one has to keep that in mind when you're doing this. One of the biggest obstacles to having widespread sort of application and use of these methods are the current generation, you need to measure every variable in the equation. If you're doing equation learning, that means you have to measure every variable or state variable you expect to participate in the equations.
Mm.
If you're doing parameter estimation, that means whatever model you have to be able to measure everything. That's a problem in something like this, right?
Oh.
SIR models, I mean, so I was on the COVID modeling team for the state of Colorado, and there was one data stream that was
Mhm.
reliable, the hospitalizations.
Mm.
Every day there was a census of how many people were in the hospital in this whole state who had COVID. At 4 o'clock, they sent out the spreadsheet of this. But you didn't get, the number of people who were infected and asymptomatic. Like that's not a number you're ever going to see. So how do you deal with this?
Yeah.
So one of my postdocs, Nora, has been actually figuring out how to do this. And so say just like a simple SIR model, let's say you're measuring just I instead of S or R. Well, it turns out there's some differential elimination or differential algebra tricks that you can use to collapse this system into a single equation in simply the data you have. So you can, I mean, this is known. You can change the, SIR model into just an equation in I. It's higher order, but you can still do it. And so that's the whole point, is that there are strategies for doing this for large scale systems to collapse them into just the subvariables that you have. And so just as an example here, this is what happens where you have wall time versus relative error, different noise levels for that problem up above. We're estimating beta and gamma, and Yes. Okay. So let's look at the 20% just to sort of demonstrate what's happening. So the wall times, of course, we're faster. We're regression. We don't have to solve the ODE. That's just
Oh.
not a problem. But what you're seeing here is we're getting everything, at 20% noise. It's usually less than 10%
Mm-hmm.
in the parameter errors. Okay. Now for these pink diamonds here, these are the solution errors, right? So this is just standard MATLAB doing a system identification and forward solver, tweak the parameters, etc. It's going fast. It's not, crazy. It's, less than a second even. But here's the thing. I'm only showing you 40% of the initial guesses we tried. 60% of the time, it did not converge or it failed to converge because that 20% noise level, it was unable to recover the correct parameter at all. And it would wander off to something that was completely unrealistic, and the ODE solver itself would not solve because it was wrong. And so here's the thing. This is solving a regression.
Mm,
There's no initial guess. You
yes.
just solve it.
Uh-huh.
So yeah, okay.
Uh,
Yes, there was one case here where it blew us away by the solver error, and more than likely what happened was it was just you got lucky with the noise
mm.
and you were able to solve it really fast, and the initial guess was reasonable, etc. So this is working its way through review at Bulletin of Math Bio to see this. But it's cool that there's ways to collapse the equation to do this. You just have to go into the abstract algebra world to get it to work.
So
Um,
basically, David, if I understand correctly, for the SIR model, although
mhm.
there are three variable equations, somehow you can convert it to the one variable,
Yes.
maybe high
Yeah.
order equation, right? Like
Right.
maybe third
Right.
order, maybe third, rather than first derivative, we can
Hmm.
convert it to the third order derivative of I
Yeah.
equation and then apply the weak form.
Exactly.
Wow.
Exactly. Yeah. Because see, you're going to get a third derivative in there
Yeah. But
when you
it's
do
okay.
that. But it's okay
Yeah, because
because
the
you
weak
take
form.
the weak form, so
Yeah.
it's not a
Wow.
problem.
Yeah. Right.
So that's
I
yeah,
think because
that's
without
helpful.
it, in the real world, actually using the third order derivative is crazy idea,
Yeah,
uh,
yeah,
but it's a
exactly.
weak form. It's totally fine.
It's perfectly fine. Yeah, it's a
Wow.
reasonable way to go. Um,
Oh, she's so clever.
yeah, it's very very nice. It's very nice the way it
Yeah.
worked out. Um, so the other restriction is if you have so here's the thing. You
Hmm.
look at this. There's a beta here.
Hmm.
There's a beta here, and I guess I put five, but there's going to be a gamma here, right?
Hmm.
On the recovery rate. Um, it's all linear in the parameters. And even after you collapse it, it's still going to be linear in the parameters.
Hmm.
What happens if you have something like a Goodwin 2D model where you have a P2 in the
Hmm.
denominator? Oh, that's not highlighting very well. There's a P2 in the denominator here. That won't work unless you can figure out some transform to get it to be linear in the parameters. It's not possible. Well, there's a way to do it with our approach. You formulate a maximum likelihood, and it will now be an iterative nonlinear optimization problem, but it is much easier to do than having to do forward solver based nonlinear optimization problems. And so let's look at what we're actually seeing here. So the legend says this is the output error least squares. That's the forward solver one. This is really you want to be comparing it with the green and the yellow. The green is from the Bulletin of Math Bio paper from 2023, and the yellow is this archive preprint that's working its way through review. But to a couple things, this is quite a compelling plot in the sense of the failure rate. So we basically put a grid around the true parameter and gave all the initial conditions as guesses in that grid. And of those, for pretty much every other method except the one we just came up with,
Wow.
they're failing, 20 to 30% of the time. They're just wandering off to something that's not going to converge. Whereas with this maximum likelihood estimation process, literally none of them diverge. And for nonlinear optimization, that's pretty nice. You can see here in the coefficient error, the Wendy, the green one is pretty good, but the yellow one is really, as you crank up the noise, it's really the lowest of the errors here. That's working quite well.
So
The hmm?
David, for this one, how do you incorporate the maximum likelihood for the conventional Wendy?
Well, so what you need to do is you need to write down basically like this is
Original problem. Yeah.
this one here. So the residual here, you can write this down as a if you know that your data is normally distributed, you
Mm,
can write down a probability density function
okay.
that is in terms of the residual and then the covariance.
I see.
And so you could write down a likelihood function
Okay.
using the making the assumption about normality.
Oh, okay.
It turns out you can also do it for log normal as well. That's
I
pretty
see.
straightforward to write that down.
So rather
So,
than you serve the regression problem, maybe you
right.
just find the maximizing the likelihood
Hmm.
function of this
Yes.
form. Okay.
Yeah.
Got it,
Yep.
got it.
Yeah. Now it gets this one is a little bit fancy here because to get the optimization going, we needed to be able to take the gradient and the Hessian, and so there's a lot of automatic differentiation going on inside this code that the grad student Nick Rummel did. So it was sophisticated, but it's still at the end of the day a pretty straightforward nonlinear optimization problem that goes pretty fast. So. Actually, sort of, I was going to show you. So, what's really interesting, which we don't really understand this. So, yellow is from this paper. The brown curve here, what we did was we took the output from the maximum likelihood estimator and used that as an initial guess for the forward solver, the solution error approach, the conventional approach. And while the parameter estimates did not, they were not the best in the world, what did end up coming out as the best was if you took the parameter estimates you got from this two-step estimation and used it in actually seeing the forward simulation error. So in essence, what it was doing was it was then finding parameters that were specific to the discretization method you used so that you would get the best prediction error. So it was a very interesting. So you can see the brown error here. This is basically prediction error, and you can see that as the noise goes up, that one is the lowest, and even it does better than using the parameters in the from our maximum likelihood estimation. Is that sort of that two-step clear what I'm suggesting here?
Hmm?
Okay.
So,
All right. Yeah.
what
So
about
that's
everyone? Is it clear for everyone? If you have a question, please.
okay. Well, I'll also answer them at the end.
Hmm.
Okay, so quickly here, I know I'm running out of time a little bit. This works also really great for PDE estimations. This is basically this is this Kermode-Sivashinsky that's awful. You noise it up. You can estimate the parameters in fractions of a second on a laptop. This is something we're working on right now. Um, One of the really awesome things about this is that there is a fairly complete theory that goes along with it. And so if you're from a biology side, all you care about is in what sense does this parameter here, as a function of the number of data points, converge to the true parameter as that number of data points gets large. Just asymptotically, don't worry about the theory. This is the picture that shows it. So this is another PDE here. Here's the solution. Here's the noise. This is what kind of the test functions look like as you're looking down on it. And you can see here for different noise ratios, even all the way up to 100% noise, as you get more and more data, the probability of discovering the correct equation collapses to 1. So what we have now is a fairly extensive theory about the discoverability classes, as in what is the set of equations that we know if that's the equation that's there, we'll be able to discover it.
Hmm.
And it's basically what it ends up as, which is kind of cool, is most of mathematical physics. Is it's all it is up to polynomials of order 2 and then any order derivative you want. And most of mathematical physics fits in there. I don't know about math biology or not, but as long as you're staying below order 2 polynomials, you're fine. And
Yeah.
then whatever derivatives you want. 10th derivative doesn't matter. We can do that one. Just need enough data. Okay, so it's an interesting result. It's not, complete. There's lots of other things to do, but it's kind of neat that it does fall out pretty straightforward. Okay, so summary here. We have equation learning. we have parameter inference. Right now, it's on the Math Bio, the GitHub for CU in our Math Bio group. We have MATLAB, Python, Julia versions of these things, and well as a R that's almost. I just saw the student gave me a demonstration today, so it's actually working and is in actually calling a C++ code, so it's very nice and fast. And then yeah, so all of these are the first three are linked off of the Math Bio site. The last one will be sometime in the next few months. Um, One of the things that I wanted to just mention here is that since we have started doing this weak form scientific machine learning, there has sort of a consensus has emerged that this is really a compelling way to do things, and there might be other areas where looking at the weak form from this opposite point of view would be helpful. And so, even in some of the stuff from the UW group where the Cindy came from, they proposed this ensemble Cindy, and if
Yeah.
you look closely in their tables, the ensemble weak form Cindy is the one that performed the best. So,
Uh-huh, uh-huh.
I mean, the ensembling is doing something different, but
Uh-huh.
it's just interesting. Another one that's really interesting is this one. So this is this group out at City of Hope in California, and they're working with perfusion dynamics and dynamic contrast enhanced MRI images, so time series MRI data. And basically, the whole point is if you put someone in an MRI machine, give them a contrast, take time series, you can use the weak form to estimate the spatially varying perfusion coefficients to get you an idea of where the tumor is. And so it actually works incredibly well in some of these data here. So I was just going to point those two out. But then I'll just finish up briefly here. So this is where things started was this joint NSF NIH grant that I had, and then it has been surprising how many different areas that it has applied to. We even have a fusion grant that we've been working on here. So it's and the group has kind of exploded because they don't just give you money and then let you keep it. You have to pay people. So there's a bunch of people, and this is where all these people are coming from that are being paid off these various funding sources. So briefly here, I'll just wrap up with the references. If you are looking for a 30,000 foot view, we got an
Uh-huh.
article on the front page of the SciM News in October last year.
Mm-hmm.
If you want a more technical
Uh-huh.
introduction, there's
Uh-huh.
a chapter in this Handbook of Numerical Analysis that
Okay.
was published last year.
Okay.
These are a lot of the things that have come out from ODEs, PDEs, different inorganic particle systems, reduced order models, even cold atoms,
Mm-hmm.
magnetohydrodynamics, and some other things. So, from a biology perspective, I want to say here's the things that probably are going to be the most interesting. So, check out, of course, the broad overview. These two, the ODEs and the PDEs, are pretty. These were sort of, we were learning how to do it too. So these are nice and introductory pedagogy. Here's the Wendy paper and Bulletin of Math Bio. And then most recently, these are the latest publications we have on. We have actually leveraging the weak form to do identifiability. You can do
Oh.
identifiability computations, practical identifiability, incredibly fast.
Oh.
I didn't present them here, but that's where Nora's work has gone. The other postdoc, Rainey, is doing learning structured populations. So he's got some really nice efforts there. And then April, her basically she's got on how to choose the test functions. She has some very, I wouldn't say complete, but it's about 30 pages of analysis of exactly how one can choose test function radii and powers of the smoothness. And so, okay, that's all. Thank you very much.
Wow.